Okay, this is section 13.4, which is going to be about double angle identities and half angle identities. In the last section, we talked about sum and difference identities, so now we're going to talk about what we call double angle and half angle. And sometimes we can use these to find the value of a function that's twice an angle or half of an angle that we're familiar with. So for example, if I need to find something having to do with, let's say, 120, even though that's one we already know, if I know something about half of that angle, which is 60, so I would be able to use these identities. So here are identities that are true for all values of theta. These are called the double angle identities. So the sine of twice some angle theta is 2 times the sine of that angle times the cosine of that angle. If I know the cosine of 2 times an angle, there's 3 different ones I can use. Cosine squared minus sine squared, 2 times the cosine squared of theta minus 1, and 1 minus 2 times sine squared of theta. And those all kind of come from each other. And then if I know the tangent of 2 theta, 2 times some angle theta, then 2 times the tangent of that angle over 1 minus tangent squared of that angle is my identity. So we're just going to practice with some of these. Let's take a look at our first example here. We're going to find the exact value of the cosine of 2 theta if I know that the sine of theta is 3/4 and theta is in the first quadrant. So here we're kind of doing things that we've done before where we were finding exact values in section 1. We're just going to do it with a double angle formula. So here is one of my double angle identities. Why did I choose this one? Because I know something about sine. That's going to help me solve for the cosine of 2 theta. So I plug in what I know for sine, which is 3/4. 3/4 squared is 9/16, of course. And 9/16 times 2 is 18/16. So another way to write this would be 1 minus 9/8. 1 is 8 over 8, so 8/8 minus 9/8 is negative 1/8. That would be the value of the cosine of 2 theta. Okay, you guys try this one. All right, your answer here should be 7/8, using the same process as the last example. All right, here we're going to do another one, the exact value of the tangent of 2 theta, if the cosine of theta is 4/5, and again here we're dealing with theta in the first quadrant. So I'm going to use this identity first to find the value of the cosine of theta. I mean sine of theta, of course, because we already know cosine of theta. So I'm going to use this identity. Sine squared is 1 minus cosine squared. That comes from one of the Pythagorean identities. So I know that cosine is 4/5. I square it and do 1 minus that. So I end up with sine squared is 9/25. So sine is 3/5. Again, I'm taking the positive sign because I'm in the first quadrant. So now I'm going to use tangent theta to get the double angle identity for tangent of 2 theta. So I know that tangent is sine over cosine, and I have my sine and cosine values, so when I simplify that, I get 3/4. So I know that the tangent of theta is 3/4. So if I want to find the tangent of 2 theta, I use the double angle identity from the chart at the beginning of your notes. So I know I'll do 2 times the tangent of theta, so 2 times 3/4, and 1 minus tangent squared, so 3/4 squared. Simplify. Should have squared the denominator and simplified it. And then when I simplify my complex fraction, I get 24/7. Remember here we're doing 3/2 times 16/7. And that gives me 24/7. So that would be the value of the tangent of 2 theta. All right, let's take a look at the second part of example 2. This time I'm going to find the exact value of the sine of 2 theta. If I know cosine is 4/5, and again, I'm working in the first quadrant. So here's my double angle identity for sine. It's 2 times the sine of theta times the cosine of theta. So if the cosine of theta is 4/5, sine of theta is 3/5, right? We got that from the first part, from part A. We already figured that out. So I just multiply all those together and I get 24/25. Ta-da! All right, here's a couple examples for you to try. Try this one. All right, in this case, you should have gotten D, negative 1/49. And there's the work for this one. You can see which identity I started with because I know something about sine, so that's going to help me find the value of the cosine of 2 theta. Sorry, didn't mean to go quite that fast. Then I plug in 5/7, square it, multiply by 2, and then here I subtract. 49/49 minus 50/49 gives me negative 1/49. Okay, now take a look at this one. All right, your answer here should be B, which is 5 square root of 6/12. And here's the work to get tangent. And then you would use the identity for tangent of 2 theta to get to here. Although it's looking to me like maybe they meant to say here just the tangent of theta. So let me know if when you try tangent of 2 theta you get something different than this, and we'll check it. All right, half angle identities. Half angle identities are basically exactly what they sound like. So the sine of some angle divided by 2 is equal to this beautiful square root thing, plus or minus the square root of 1 minus the cosine of theta over 2. Here you can see the identities for cosine and for tangent. So let's take a look at some examples of how to use these. So I'm going to find the cosine of theta over 2 if the sine of theta is 3/5, and this time I'm in the second quadrant. So that means that cosine of theta will be negative, but that's going to come into play here in a minute. Since the cosine of theta over 2 is plus or minus the square root of 1 plus cosine of theta, I need to find the cosine of theta before I do anything else. So I'm going to use my Pythagorean identity that I always use to find sine and cosine. Plug in what I know for sine, which is 3/5. I get cosine squared is 16/25, and then take the square root, plus or minus 4/5, and I'm in the second quadrant. I'm going to take negative 4/5 as the cosine of theta. So now that I have that, I can go back and use my half angle identity. So I plug in negative 4/5, so I have 1 plus negative 4/5. And if I simplify that all, in my numerator I get 1/5. 1/5 over 2 is 1/10. That's how they got 1/10 under the radical. I'm going to rationalize my denominator. So I get plus or minus the square root of 10 over 10. Now here's where that whole quadrant thing can be a little tricky. You just have to be careful. Theta is between 90 and 180. So theta divided by 2 has to be between 45 and 90. So that means that the cosine of theta over 2, since theta over 2 is in the first quadrant, I'm going to use the positive cosine value. All right, let's take a look at this one. Here they're actually giving me an angle here instead of just saying theta. So my goal is to say, okay, what common angle divided by 2 gives me 165 degrees? Well, that's pretty easy. You just think of what 165 times 2 is, which is 330 degrees. 330 degrees divided by 2 is 165. So these are equivalent trigonometric expressions. So I'm going to use the half angle identity for sine. Looking back at the chart at the top of this page of your notes. So in this case, my theta is 330 degrees, right? Theta over 2. So the sine of theta over 2 is 1 minus the cosine of theta all over 2, plus or minus the square root of that. So here again, my theta is the angle being divided by 2. So my theta is 330 degrees. You, of course, know the cosine of 330 degrees from the unit circle, which is square root of 3 over 2. So I have 1 minus the square root of 3 over 2, all over 2. Here I'm just rewriting 1 as a fraction with a denominator of 2. Simplify the fraction, so I end up, let me show you what they did here. We had 2 minus the square root of 3 over 2, all over 2. So that's the same as multiplying by 1/2, right? Dividing by 2 is the same as multiplying by 1/2. So 2 minus the square root of 3 over 2 times 1/2 gives me 2 minus the square root of 3 over 4. And of course, I'm still under a square root. Here they're just simplifying the denominator. The square root of 4 is 2. And we can leave it like this. So I actually end up with a square root inside of a square root. All right, here are a couple for you to try. All right, for this one you should have gotten A, 9 square root of 82 over 82. And here's the work for this one. Since the half angle formula or the half angle identity for cosine involves cosine, I use my Pythagorean identity to solve for cosine, so I did that here using my sine value. Then after I know cosine, I just plug into the half angle identity. I end up with plus or minus 9 over the square root of 82. And when I multiply the numerator and denominator by the square root of 82, I end up with answer A. All right, try this one. Okay, your answer here should have been B. All right, and here's the work for this one. In order to use the half angle formula, I recognize that 157.5 is the same as 315 degrees, which is a common angle that I know something about its sine and cosine. It's one of my unit circle angles. 315 degrees divided by 2. So here my theta is 315 degrees. So I use the half angle formula. 1 plus the cosine of theta, cosine of 315, that's the square root of 2 over 2. It's in the fourth quadrant, so this is positive square root of 2 over 2. Common denominator, so 2 plus the square root of 2 over 2 divided by 2 is like multiplying by 1/2. So that's how I end up with my denominator of 4. The square root of 4 is 2. And so I end up here with plus or minus, but I'm talking about 157.5. That is in the second quadrant where cosine is negative, so that's why I choose the negative value. All right, we're going to skip down to example 5 to make sure we have time to verify identities here in this video. So here we're going to verify that the sine of theta times the quantity cosine squared of theta minus cosine of 2 theta equals sine cubed of theta is actually an identity. So here's my original equation. Since I'm verifying, I put that question mark over the equal sign. That means I cannot move things back and forth. So look at what they did over here. Cosine squared, sine of theta, and cosine squared of theta stayed the same. I've replaced the cosine of 2 theta with one of my identities, cosine squared minus sine squared. Okay, so that's what they did in that step. And then here I'm just distributing my negative, so I end up with cosine squared minus cosine squared plus sine squared. And now, how did we get to here? Well, cosine squared minus cosine squared is 0. So I just end up with sine of theta times sine squared of theta, which is sine cubed of theta. So it turns out that this is an identity that I can verify. All right, you guys try this one. Okay, your answer here should have been yes, this is an identity. And you should have ended up getting down to here. But the way you can do that is by distributing. So if I distribute, I end up with cosine of theta plus cosine theta sine theta, then minus sine theta cosine, oops, sorry, that went a little bit crazy, minus sine theta cosine theta minus sine squared theta equals the cosine of 2 theta. Of course, I'm putting my question marks, I'm verifying. Notice that these two terms subtract out to 0. So I end up with cosine squared of theta minus sine squared of theta equal to cosine of 2 theta. And from our identities at the very beginning of the section, we know that cosine squared minus sine squared is the same as the cosine of 2 theta. So I have verified that this is an identity. All right, we're going to back up to example 4 just real quickly. We're not going to go through the whole thing, but notice here that they're talking about a fountain in Chicago that has jets placed at specific angles to shoot into the water or shoot into the air and create different arcs. When a stream of water shoots into the air with a velocity v at an angle of theta with the horizontal, the model predicts that the water will travel a horizontal distance d of v squared over g times the sine of 2 theta, and its maximum height will be v squared over 2 times g times the sine squared of theta. The ratio of h to d, that means h over d, helps determine the total height and width. They actually want you to find d over h. So when you set that up, you get this beautiful equation. And we're simplifying our numerator and denominator a little bit here by dividing with our fractions. And when I simplify it down, I get 2, and I end up with a double angle formula that I can continue to simplify. That's basically the goal.